last day we were talking about limits of sequences of functions. We started the whole course by talking about limits of sequences of numbers and their limits, and we started talking about sequences of functions and their limits, and we did a number of examples last day. I said there's one further example I wanted to do, but I wanted to show something graphically, and so I produced the graphs so that I can show them on overhead rather than me hand drawing them. So the sequence that I want to look at is the following. The sequence of functions are equal to n squared x over 1 plus n cubed x squared, x greater than or equal to 0. The reason I want to show graphically, because personally I'm a visual person and I like to see graphs, but sometimes graphs can be actually misleading. Okay? We can solve this problem in one line, algebraically. If you want the limit of this sequence, I would suggest that what we do is we divide the top and bottom by n squared. If we do that, we have the limit as n goes to infinity of x over, dividing by n squared, 1 over n squared, plus nx squared. Correct? Divide top and bottom by n squared. And now clearly the top limit, there's no n's there, so it's x. This goes to 0, and what does this do? What does that do? Well, if n gets large, then that's going to get large. Let's pretend it's x equal to 0, so I'll come back and check that in a second. But if x is not 0, then this is going to get huge, and therefore this is going to be equal to 0. Clearly, if x is not equal to 0. So all we have to do is check out at 0, at x equal to 0, f n of 0, we put in x equal to 0, we get 0. So the limit of this, as n goes to infinity, of fn of 0 is also equal to 0. So in other words, the limit exists, and it's a 0 function. Now that did not take too much algebraically. What I've done, I'll show you graphically, is to draw graphs of these functions. So there's some graphs of these functions. You can see the f1 function, the f2 function, the f3, the f4, and the f5. Now remember that an infinite sequence of functions represents an infinite sequence of numbers, but a whole bunch of them, one for every value of x. So if I went, say, to x equal to 1, I went to x equal to 1 right here, then the sequence of numbers would be, you look at f1, okay, a dot would be there, then f2 dot, f3 dot, f4 dot, f5 dot, it would all approach 0. And that's kind of obvious anywhere over here. The numbers, the sequence of numbers, they're all getting smaller, smaller, smaller. But if you went, say, to this value of x, and you looked at it, so you draw a vertical line, say, right there, to intersect all the dots. There's that first one, there's f1, f1, that number of x. Then f2 is that one, f3, okay, is that one. F4, oh, so that was F, so there was F1 of that number, F2 is that one, that went up, oh, now it's starting to come down. So back in this region, the numbers don't just decrease to 0, they increase for a while, and then they decrease. Question is that how it's going to happen? I suppose you take an x in here, really close to 0 here, and say, there's the first one, there's the first dot, second dot, third dot, fourth dot, fifth dot. Hey, they're getting bigger! If I drew more functions, would they eventually come down? The answer is, yes, they would. All right? They will eventually come down, because these maxima on these curves continually, they do rise, but they continually, the maxes, relative maxes, move this way. And eventually then these dots would come back down once you were past where that maximum is, right? But that is not so obvious as the algebra was here. Okay? So geometry sometimes helps, but here, I don't think it does. Perhaps we should phrase it that this one is lecture 3, right? So what we've considered so far is section 10.1 and 10.2. We've talked about sequences, numbers, and sequences of functions. Sequences are simply lists. Lists of numbers or lists of functions. What we now want to go to is section 10.9. We're going to start talking about series. 10.9 talks about infinite series of numbers. Concept is easy. But if there's anything that I've got to tell you, is get these two words straight. Distinguish clearly between a sequence and a series. If you went out and talked to somebody in the street, they probably would think they're the same. Mathematically, however, they are distinctly different. Right? Definition. An infinite series of numbers is the sum of the terms in an infinite sequence of numbers. So in other words, you start with a sequence, which is a list, commas between them, and you insert instead of the commas, plus signs. So if I give you a sequence, C sub n, the series that comes from it is C1, C2, C3, dot, dot, dot. Simple enough idea, right? Simply add them up. Instead of putting commas between them, you add them. So again, sequence, list, series, sum. Don't mix them up, right? Let's write down a few of them. From last day, we had some sequences. Suppose I give you the sequence 1 over 2 to the n. We had that one last day. It gives rise to the series a half plus a quarter plus an eighth. And you could read this in single notation as summation n equal 1 to infinity of 1 over 2 to the n. Love single notation. You got used to it first year. Right? We'll be using it a lot. All right? So there's one. We had last day also the one n cubed. It was a sequence we dealt with previously. That one, okay, which is 1 cubed, 2 cubed, 3 cubed, dot, 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 dot. Right? It gives rise to the series summation. Well, that's, see, bad already? That's bad, right? Right? This is a sequence. What I do, I put in the plus signs. Bad, 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 right? So I should say, oh, okay, this is not saying equal, says gives rise to. Okay? So n cubed gives rise to this series, and it goes into infinity of n cubed. We had this one, minus 1 to the n plus 1. That gives rise to the series 1 minus 1 plus 1 minus 1, dot, 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 dot. which is equal to summation, n equal 1 to infinity, minus 1 to the n plus 1. And then finally, we also had n over 2n plus 1. That sequence, it gives rise to the series, again, terms n equal 1 to infinity, n over 2n plus 1. So those were sequences we had the other day, and now out of them come series. We simply add up the terms in the sequence to produce a sum. Now that looks just wonderful. However, it doesn't mean anything, right? Suppose I said, okay, go do it. You're supposed to add up an infinite number of terms. Well, I'm sorry, I don't care how good you are, how good your calculator is, how good your computer is. The only way you can add up an infinite number of terms in a finite amount of time. So at the moment, even though we've defined what an infinite series is, we really have defined something that has no meaning. And so what we've got to do is say, now, what does it really mean? Well, this first example is really a key. This one, all right? So at the moment, no meaning. Must give meaning to whatever we're talking about here. So let's look at the first one. Let's plead ignorance and say, I realize you can't add them all, but just for fun, I'm going to start adding them up. I'm going to denote by S1, so that's this one here. S1 is simply the first term, 1 half. By S sub 2, I'm going to mean the sum of the first two terms in the series. That means 1 half plus 1/4. But everybody knows that that is 3/4. S sub 3 is the sum of the first 3 terms. So that's this one plus this one plus this one, which really means this plus this. 3/4 and 1/8, that's 7/8. S4, add on the next one. The next one is 1 over 16. 7/8 and 1 over 16 is 15 over 16. But by now you say, something's happening here that is very interesting. That no matter how many terms of this series I add together, it will never get bigger than 1, but it gets as close to 1 as I want. In fact, you could actually write down a formula. You write me a formula for S sub n. Based upon what you see here, what would you write? Look at the bottoms. What's a formula for the bottoms? Is it not 2 to the n? What are the numerators? They're 1 less. 2 to the n minus 1. You could actually write that as 1 minus 1 over 2 to the n. There's a formula for S of n. The sum of the first n terms. This is a formula of the sum of the first n terms in this series that came from this sequence. Now let's ask, what happens as n gets huge? We surmised here, but this is telling the story completely. As n gets bigger and bigger and bigger, this thing gets bigger and bigger and bigger, this thing gets smaller, 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 it therefore gets closer, closer, closer to 1, and it's never bigger than 1 because you're always subtracting. So could we not say then that the limit as n approaches infinity of S of n is 1? The limit of that sequence, right? This is the limit of a sequence. We actually call these, this is called the nth partial sum. It's the sum of the terms of the series up to including the nth one. And we've shown the limit of the sequence of partial sums is 1. That the more and more terms we gather together, the closer and closer and closer the sum gets to 1. Right. Okay. That's the way we're going to define series in general. To define what a series is, So we take this and extend it to all series. Extend this idea to all series. That is what we say. Suppose given then, oh, I want to refer to these ones. What was this? This was in cubed. This one was minus 1 to the n. And this one was that. Definition. Given a series summation n equal 1 to infinity c sub n, define its sequence of partial sums. S1 is equal to C1. S2, sum of first two terms. S3, sum of first three terms. Down to down. S sub n, sum of the first n terms. Produced from this series a sequence of partial sums. Notice then that there are really two sequences here. There's a sequence of terms from which the series arose. Now we produce from the series a sequence of partial sums. If the limit as n goes to infinity of S sub n exists, if that sequence has got a limit, call it S, we say that S is the sum of the series. And we write summation n equal 1 to infinity of C sub n is equal to S. So we now know what you mean by an infinite series. You're all interested in whether does it have a sum. And the answer is, here's what you will do. If you want to know whether a series got a sum, you form a sequence of partial sums. You ask that sequence, do you have a limit? If the answer is yes, you call that the sum of the series. If sequence does not have a limit, we say series has no sum. Or we also say that it diverges. Just like we said, when a sequence doesn't have a limit, we say that the sequence diverges. So talking about infinite series is talking about its sequence of partial sums. So let's go back and take a look at these other three examples that we got on the board and ask them, do you have a sum? So we've already done this one. Let's look at this one and ask, you, if I were to form your sequence of partial sums, would it have a limit? That means you write down the first term, and then you add the first two terms, then you add the first three terms, and you add the first four terms, and you keep doing that and that. Is it settling down? And the answer is no. Clear? No. Those partial sums just get huge. Right? So S sub n limit does not exist, therefore no sum. Next one. What about this one? Let's write out a few terms, like I often suggest. 1 minus 1 plus 1 minus 1 plus 1, da 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 da. Does that series have a sum? Some people would say to me, yes, it's 0. Because they all cancel each other. But don't do strange things. I gave you a definition. You use it to find out what is S of 1. You're supposed to look at the sequence of partial sums. That's 1. What's the sum of the first 2 terms? That's 0. What's the sum of the first 3 terms? That's 1. Sum of the first 4 terms? 0. Does that sequence have a limit? Answer, no. Therefore, no sum. Right? Limit n approaches infinity of S of n does not exist. Therefore, no sum. All right. So don't do strange things. I give you a definition. You use it. Let's look at the fourth one. This one. What do you think about this one? Do you think that series got a sum? Now remember, the sequence of terms got a limit. That was a half, okay? Oh, that's the key. If the terms in this here, if these terms are getting closer and closer and closer to a half, it's like when you get y out there, it's like adding a half, and a half, and a half, and a half, and a half. Is that going to add up? No. All right? So just thinking about that idea, this one's got no sum because terms approach a half. How can adding up a whole bunch of halves settle down anything, right? So when you form the sequence of partial sums, it couldn't possibly approach anything because it's like adding a half and a half and a half every time you take a step. Next term in the sequence of partial sums. Clear? So there's some straightforward examples, right? There's a couple series that are very, very important to us. In particular, the one that I want to consider now. It's not a series, it's a whole bunch of them, but they all have a common property. And hence they get their name from this property. In fact, two of the ones that I just erased, this one and this one, will turn out to be of that kind, called geometric series. It is surprising how many applications, and if you go to section 10.9 and do some of the applications, it is surprising how many applications give rise to geometric series. And that's why they're so important. So let me tell you what they are. A geometric series is one in which every term is obtained by multiplying the previous term by the same number. So what you've got is you got a first term obtained out by A, and then the next term is going to be obtained by multiplying this by something, let me call it R. Then the next term is going to be obtained by multiplying this one by that same R, so it will be AR squared. The next one will be AR cubed. And on and on and on it goes. That's called a geometric series. Every term obtained by multiplying previous term by same number. And that number is called the common ratio. You can see perhaps why they call it that. If you were to take this one and divide by that one, you would get R. If you take this one and divide by that one, dividing is ratio, that one divided by that one, R. That one divided by that one, R. Hence we call them the common ratio, because you always get the same number, and we're doing ratios or divisions. This one, is the first term of this series. So you can have anything for A, except you don't want to put in 0 because that would be kind of stupid. If you put in A equal to 0, then there's not much there. So A generally not 0, but R could be anything. So you got a whole raft of geometric series. Make any A you want non-zero, any R you want, and you get a geometric series. Would you agree that this one is geometric? Remember the terms were a half, and a quarter, and an eighth, and on they go. Is every term obtained by multiplying the previous term by the same thing? The answer is yes, it's a half. So the common ratio is 1/2. Is this one a geometric series? Yes. The common ratio is -1. Every term obtained by multiplying the previous one by -1. Not geometric, not geometric. Right? So 2 out of those 4 were geometric. Is this geometric? And the answer is yes. First term is 3, and the common ratio is 4. That's geometric, right? So there's lots of geometrics out there. The question is, do geometric series have sums? And the answer is, it depends upon R. So let's go on the discovery process and see if we can figure out for what values of R geometric series converge and for what values of R series diverge. How do we tell? There's only one way. I'm only giving you one way to decide whether a series diverges or converges, and that is look at its partial sums. So let's look at the partial sums. S1 is equal to 1 times E. S2 is A plus AR squared. S3, no, it's not AR squared, it's AR. AR squared. S of N, AR squared up to AR to the N minus 1. There's the first N terms added together. If I want to discover whether this series has got a sum, I have to say, sequence, do you have a limit? And at the moment, I can't tell. What I've got to do is I have to find a simple expression for this. Right now, I can't do anything with it. So I've got to find something to replace that by so I can say, what is a limit as n goes to infinity? The trick is to do the following. Suppose I multiply this by R. Just multiply this whole thing by R. Left side, right side. I multiply the right side, I multiply every term by R. Suppose I now take these two lines and I subtract them. I take this one minus this one. I would have Sn minus Rsn is equal to. But everybody will notice that when you take this minus this, there's a lot of cancellation. Like that one, that one, that one, that one, that one, and that one. The question is, who survives all this cancellation? Well, I think you're going to agree this one is going to survive. And if you think about it, what's sitting right before that sign, right there, is that guy there. So that one will cancel that one, and you'll have this one left, minus AR to the end. So what do I now have? At least now there's no more dots. Suppose I take it on the left, I factor S of N, I go to the right, and I factor out A. Then I would have 1 minus R S of N, A, 1 minus R to the N. Let us now divide by that. S of N is equal to A, 1 minus R to the N, over 1 minus R. So there is the sum of the first n terms of the geometric series. No matter what it is, no matter what R, you give me any R, you give me any R, and you ask me, what's the sum of the first n terms? I simply have to take and plug in the A and the R and the N and say, there! Except there's one problem, huh? This is provided R is not equal to 1. But if R is equal to 1, well, let's leave that for a second. We'll come back and talk about that one in a minute. All right, so let's assume for the moment that R is not 1 and ask the question. What is the limit as n goes to infinity of this S of n? If it exists, that's what we're going to call the sum of the series. If this limit does not exist, we say series, you do not have a sum. Well, the n is only here. No n, no n, no n, no n. There's the only thing that's not an n in it. So let's ask the question, what happens to r to the n as n gets huge? And we've had enough examples, I think, on the board already when we're talking about sequences of numbers and functions to decide what that is. It depends upon R. Would you agree with me that if minus 1 is less than R is less than 1, put a number in there between minus 1, a half to the n, and then n get huge. That's like a half times 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 a half. Answer 0. Put in minus a quarter. Minus a quarter times minus a quarter times minus a quarter. Tick, 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 0. Would you agree then that this is 0? Or any value of n r between minus 1 and plus 1, not inclusive. Right? What if r is equal to minus 1? If r is equal to minus 1, you've got minus 1 to the n. Minus 1 to the n, well, that means it goes minus 1 plus 1, minus 1 plus 1, minus 1 plus 1, no limit. Right? So it does not exist if r is equal to minus 1. What if r is larger than 1? Put in 2. 2 to the n. N get big. 2 squared, 2 cubed, 2 to the 4th, no limit. What about minus 2? What if r is equal to minus? What? Does not exist. What if r is less than minus 1? Put in minus 2 to the n. Let it get big. Minus 2. Minus 2 squared. Minus 2 cubed. Minus 2 to the 4th? No limit. Does not exist. Who's left? The only person left is r equal to 1. All right, but we're going to do that guy separately. Let's do it now. All right? Well, let's do it separately. Okay, so can we see here that this limit, all right, let's see. We're talking about this guy now. We're going to see. If we're between minus 1 and plus 1, you're going to 0, where you have a over 1 minus r. Minus 1 less than r less than 1. Great. If r is any other value, all right, except we haven't talked about r equal to 1 yet, all right, but for all other values outside of here, except for after, we also going to say, all right, what about other values? For every other value other than these, we've got them all here except minus 1, or except r is equal to 1. So it does not exist. What about r equal to 1? If r is equal to 1, then what's your series? A plus A plus A plus A, right? No. Could we write that in here and say, the sum of the first n terms is if r is not equal to 1, and what is it if r is equal to 1? A plus A plus A plus A, would it be then n times A? And so now what's the limit over here? Right? What's the limit as n goes to infinity of that thing? Does not exist. All right? So for every other value of r other than these ones, there is no limit. Could we say this? Would that wrap our walls? Less than and equal to. That takes care of them all. So geometric series then have sums. Only when the common ratio is between -1 and +1, not including. And this is the sum. Any other value of r, no sum. So we can write then the following. That a geometric series has sum. A over 1 minus r, provided -1 is less than r is less than 1. All right. So geometric series only have sums when the common ratio, the number that you get by multiplying terms successively, is between -1 and +1, not including. All other geometric series, no sum. For instance, and be very careful. What is that? Back over here. First term. What is it? Common ratio. People are going to mix up, they're going to mix up this. I've seen so many people go wrong. Remember that A is the first term. For instance, the one we had on the board earlier. Summation. N equal 1 to infinity. 1 over 2 to the n. That was one we actually worked with to figure out what it really means to be a series. We said a minute ago, that's geometric. Common ratio, aha. So sum is going to be first term. What's the first term? You get it by n equal 1. Aha. Common ratio, aha. Half over half, 1. So we discovered a little while ago? The answer is yes. We did the partial sums and we got we had this one on the board a minute ago. Summation. N equal 1 to infinity. -1 to the n plus 1. I said it was geometric. What's its common ratio? -1. Therefore, no sum. No sum. Diverges. Does not have a sum. All right? Some geometric series have sums, some don't. Depends upon what the common ratio is. Strictly depends upon the common ratio. I'm going to be doing a number of examples of these ones shortly. There's one other series that I would like to introduce you to. It seems to crop up in a lot of places. You might see it someday, you might not. But if you ever run into things called Bessel functions, this guy rears his head all the time. It's called the harmonic series. There's only one. There's an infinite number of possibilities for geometric series depending on A and R. Harmonic series, one and only one, it is this one. That's called the harmonic series. And the question is, does it have a sum? And the answer is no. It does not have a sum. But the only way I can demonstrate that is to show you the sequence of partial sums and show you that that sequence does not have a limit. So that's what I propose to do. I'm going to look at a sequence of partial sums. S of 1 is clearly 1. S of 2 is the sum of the first two terms, which is 3/2. Bigger. It's clear, isn't it, that these sequence parts, they're going to get bigger and bigger and bigger because you keep adding more and more terms. The question is, they're getting smaller, smaller, smaller. Does adding smaller, smaller little things mean it settles down, or does it going to get big? The answer is I'm going to show you that it gets big. I'm not going to look at S of 3. I'm going to look at S of 4, which is the sum of the first 4 terms, which is the sum of the first 2 terms, this 3/2, plus a third, plus a quarter. quarter. Agree with that one? Would you agree that this is bigger than 3 halves plus a quarter plus a quarter? All I've done is replace that third by a quarter, which is a third is bigger than a quarter. This is bigger than this. So the sum of the first 4 terms is bigger than this, and this is 3 halves and another half. That's 4 halves, which is 2, but I prefer to leave it as 4 halves. You'll see why in a minute. I'm going to look next at S sub 8, and you can see the guys that I'm looking at. 1, 2, 4, 8. Next one probably going to be 16. But let's look at it. That's the sum of the first 8 terms. Would you agree that that's S4 plus 1 over 5, 1 over 6, 1 over 7, and 1 over 8? That's what the sum of the first 8 terms is. The sum of the first 4 plus the 5th, the 6th, and the 7th, and the 8th. Would you agree that that's bigger than 4 halves plus 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8? All I've done is replace this by that, but that was bigger than that one according to this. This one is bigger than that one. This one's bigger than that one. This one's bigger than that one. And those two are the same. So whatever the sum of the first 8 terms is bigger than that. But an 8 and an 8 and an 8 and an 8 is a half. So this is equal to 5 halves. Now I should have put a greater than here, and that should be an equals, okay? Right? Can you guess, if I go look at S sub 16 and do this same thing, what I'm going to get? I think I'm going to get it bigger than 6 halves. And the answer is yes. If I look at S sub 32, bigger than 7 halves. Does this show that the limit, as n approaches infinity, S sub n is infinity? That the terms in the sequence of partial sums just get bigger and bigger and bigger and bigger. They don't get big fast, but they do get bigger. I can take enough terms in this series to make this sum bigger than 100. It takes a large number of terms. I can make it bigger than 1,000, and that would take a tremendous number of terms to make that bigger than 1,000, but I could do it. So the harmonic series has no sum. This series diverges. And yet I said at the beginning, this series seems to crop up in a lot of places. Well, it's not the whole series, but its partial sums seem to crop up in a lot of places. And the partial sums all exist. It's just you cannot add up the series as a whole. Let's do one more example of geometric series. Is this geometric? I think I had this one on the board a minute ago, if I don't, it doesn't matter. 3.4 plus 3.4 squared, 3.4 cubed, 3.4 to the fourth, and so on and so on and so on. Is that geometric? Is every term obtained by multiplying its predecessor by the same thing? The answer is yes. Multiplying by 4. No sum. No sum. Geometric common ratio, bigger than, what would make it 3.25? 3.25 squared. 3.25 cubed. It is still geometric, agreed? But now the common ratio is a quarter. So now it's got a sum. And what's the sum? It's the first term, which is 3/4 over 1 minus the common ratio, 1/4. So it is 3/4 over 3/4? 1. It's 1. Didn't plan that. It's 1. So the more and more terms of that series I take and add together, the closer and closer and closer the sum will get to 1. Never gets there, right? Realize when you see this, right? You can't add them all up. What you mean by saying this is, if you add more and more and more of them together, you get closer and closer and closer and closer to 1. I'll be saying this 20 times over the course of this topic. Is what do you mean by the sum of a series? Answer, limit of sequence of partial sums. Add and watch. It settles down, that's a sum. It doesn't settle down, There's no sum.